All right, so welcome to the 2020 Term 2 live stream exam preparation. We'll be going over the 2020 Term 1 exam, which was done on Maple TA, just like this current exam will be for 2020 Term 2, that is. Now, before we actually go take a look at the old exam, I want to point out there is a section on Moodle, so section 6, called the End of Term Examination. Well, we'll talk a little bit more about that in a second, I think. So let's just talk about this information first. So there is a booking page, which I actually haven't had a look at, but I've heard people talking about. I believe you have, the exam duration is 3 hours, but I believe when you're booking in a 2-hour window to begin. So when you see the booking, it should be for a 2-hour window. I think most people should have booked already. If you haven't, you'll need to contact somebody about that. Now, this should be the most up-to-date information about the exam. It will be different from the information you see in the past exam because, of course, that was for a past exam, so it's different information. So somebody was asking, yes, the questions will be similar, and we expect you to do a similar amount of work to what you've done in the past. And that being said, it is open book. So we are allowed to assume you have access to resources which you otherwise wouldn't have. I wouldn't say it's going to be the same, well, yes, the same difficulty, but the style is going to be slightly different just to sort of adapt to the environment we're currently in. Term 1 exam was a pen and paper exam, essentially. It was done, you were doing it pen and paper and just using Maple TA to get your answers to us. Now, so as you'll notice with the questions we're about to do, we actually do tell you beforehand what the points are worth for each question. So if you do a question, how many points you can expect to get as a maximum for that question. You, of course, must sign a declaration saying that you're not going to be going for any outside help. Sorry, I'm trying to zoom in. Come on, mouse. Come on. There you go. Close this menu. So yeah, I think it's one thing people were asking about. You can use your own notes during the exam. It's not a closed book exam. You have to use whatever resources you have. You can use any handheld calculator, and I'm hoping that's the most you're going to need for this exam. You can use software like Maple via My Access, but this is not necessary. The questions we've been designing have been designed so you shouldn't be disadvantaged if you don't have access to Maple. And of course, what I really expect for you to need for this exam is a handheld calculator, pens and paper, and your knowledge of the course material. That's all I think you need. That last part is the hard part because it's not something you can easily just buy, for example. Do you have any comments you want to make, Sean, before we look at the questions?
No, I don't think so. There was a question in chat about can we expect the exam to be harder just because it's open book. I mean, I think it all comes down to how you interpret something being more difficult or not.
Yeah, well, I should say this. Every
Yeah,
exam I've seen people do, it's always harder. You find it more difficult than the previous one. Like, no matter how many examples you look at, it's always something completely new when you get to the exam. So you have to be prepared to deal with new things.
Yeah, that's very true. Yeah, the only thing I would really sort of rule out is that you can expect we won't be asking you to, literally write out a theorem you've seen before, because while that would be fair game for a closed book exam where we're asking you, do you remember this theorem? We expect you to have all the theorems at your fingertips for this sort of exam.
I expect people may find this hard, but yeah, I've always heard reports from every time an exam's finished that people found the exam hard. So that's just the nature of examination, I believe. Okay. So actually, let me. Do you want to say anything about these instructions?
Not particularly, just to make sure you've read through them in advance, because I expect they'll be pretty much exactly the same. So this first question is not really a question; it's just an instruction page, right? And I suspect for the term 2 exam, it'll be identical. I mean, so if you've read through it now, you won't have to worry about having to read through an info dump just before you start your exam when you're actually sitting it. But yeah, it probably is worth mentioning the little box at the bottom. But
yeah, so this is something different. So most of the information, this information will pretty much just be a copy of what you're seeing in Moodle. So read through the information in Moodle first. That way you're aware of it. Something vanished. There it is. So the only thing that's different is you have this box. So if anything is happening during your exam, it's up to you to try and document it. So if there are technical issues or if I guess anything you want to document, you can document it in here and it'll be sort of kept with your exam. It'll be stored on Maple TA. I also recommend taking screenshots and things like that. Try to make sure that you if anything happens, you want to have a good record of what happened. Can you type it in your own LaTeX editor and copy it into the essay box? Yes, that should be, well, I mean, what do you mean by copy it from where? Copying it from the LaTeX edit, like the plain text? Because this thing, it won't render any mathematics. It doesn't render LaTeX. So anything you typed in here will just be seen as is. Oh, they do? Is that true? They support the backslash. I kind of don't recommend it because if you mess up your LaTeX, then you're going to have to try and fix it.
Josh, did you want to demo what it's like to use the equation editor for that sort of essay box question?
Yeah, sure. So I'm going to get up to that when we get up to that, but we can do it now. Where is that question? Yeah. So I think what Shinran was pointing out is you can say things like this, but personally I don't recommend it because using LaTeX is a nice way to get hard to read things, which I think if I go next and come back, it has rendered. Okay. I don't recommend that. So what I do recommend is perhaps using the equation editor. So you can just type things in here. It's fairly intuitive. I would recommend practicing using it if you want. That being said, I believe there were issues last term where some of these equations were hard to view by the markers, and we had to do a lot of work just to get the information out. It was possible, but it was annoying. So that's also why I don't recommend it, because you might just make someone's life a bit hard. So, so you can type. So you could use the. I cannot type.
Yeah, so I was going to say the exams, the students who did the exam last term, not too many really bothered to use the equation editor. And I think that the questions themselves were kind of written so that if you wanted, like, that you wouldn't have to use the equation editor too much, if at all. So what I mean by that is most of the answers that I read through were just using plain text, like Josh has written in the second to last line, right? And that's readable enough. And you were never penalized for typing like that instead of any other way. And so since it's a bit simpler to type up usually, and a bit easier for the marker to read sometimes. I would just recommend going for that. But if you prefer, if you think it's more readable or whatever, you're welcome to use the equation editor. The other thing I keep in mind is that it can be a bit more time consuming to use.
Yeah. Also, I've just gone through and formatted this. You don't have to format it like this. I would say it is a 3-hour exam. If you've gone through 2 hours and you're actually completely finished already, then I would probably go back and think about at least splitting up. Well, try to make sure your paragraphs are distinct. The only thing I probably would do is start. It might actually be easier just to start each sentence on its own line, just to make it easy to see where the sentences start. But this sort of like, I wouldn't worry about the way it looks until the very end. Worry about what you're writing down, and then when you're at the end, then you can think about making it look nicer. And again, I don't really recommend the nice equation editor. As nice as it is, it's just not. It takes a bit longer to use.
Also, just to answer a couple of other questions, don't think of this as the same sort of marking scheme as the assignment, right? There are no marks allocated to niceness of presentation or anything like that. So you could write something that's a complete mess, and your marker will still endeavor to read through it properly and assign the marks that you would have earned mathematically, right? That said, the other thing I would mention is use as much space as you like, right? Another thing I noticed last term was lots of students tried to fit everything to one-line explanations, or seemed afraid to put in new line characters. But as Josh is demonstrating, I mean, you have as much space as you'd like. That example, like the second example under the double line, is a lot more readable, I think, to me, both for a marker and for the student if you're coming back to that question and checking that you've written up everything that you wanted. So yeah, don't be afraid to use space.
Yeah, it's true. This is much easier for me to understand what I have written. Here I have to work a lot harder just to get my own writing back out. So I guess we'll see what we do when we actually go through the exam.
And to answer Shinran's question, the marker will see, they won't just see the plain code. They will see things you enter with the equation editor and everything. I don't know what, the example I'm thinking of when Josh mentioned sometimes they're a bit hard to read. Sometimes students would write a really long single line set of equations that would sort of run off the edge of the page. So that's the one example I can think of that was that made things a bit hard to read. Yeah, maybe I don't know if Josh is thinking of another example, but that's the sort of thing I would avoid if I were opting to use the equation editor.
Yeah. I mean, there is another way to type this as well. If you do like LaTeX, I mean, because the MATH1131 is terrible, you can do, the dollar signs aren't supported, I think. Doesn't, strange. Is it supported? No, I'm not so sure anymore. Yeah.
I think it's double dollar signs are accepted, but not single, maybe.
Okay, that's curious. So will that display? What happened there? I have no idea what just happened. Yeah, I don't think it's something weird's going on. That's why I think it's probably a good idea to maybe avoid the LaTeX if possible. I'm pretty sure that's not what yeah, it just went back to normal. It didn't actually say what I typed. This is fine. This is perfectly readable. I can understand that. I guess you want to be careful with brackets if you're trying to say something else, that's all. It's very easy to forget what things actually mean.
So Wei is asking if you try the practice exam again, do the questions change? The types of questions don't change. So everyone who sits the exam will get the same types of questions. It's the values that will switch around. And sometimes if a value is changed, then the question
conclusion.
yeah, can change completely. But yeah, that's at least how the practice exam works. I don't know what the situation is for the for the actual exam, but of course it shouldn't matter to anyone because you will only be sitting that once.
Yeah. Right, so I've generated my own version here because these versions should change unless somebody's actually fixed the randomization for everyone for this version. I don't think anyone did that. I think it's still just a randomized thing. Definitely the questions we've written are randomized. Let's see, where's this OneNote? Yeah. So I think I'll start. So question 2. Now, okay, one thing is it is called question 2 because question 1 was the instruction question. There is no marks awarded to so-called question 1. Question 2 is the only thing that's actually, yeah, question 1, no marks awarded to that. Question 2 is worth marks. We'll probably try and make the labeling a bit better for this term so you really understand which part is which. But you'll be able to see how many marks they are worth in the question. All right, so I have this complex number z, and first task is actually a very simple task. It just wants me to find the Cartesian form for z squared. Now this is a pen and paper exam, just like your exam will be too. So we'll do the calculations pen and paper and copy them all over to MapleTA, however you want to do that. All right. This one shouldn't be hard. It's an extra bracket, which is not necessary, but that's okay. I'm looking for the square of this number. Well, that seems easy enough. So I get this number squared. I'm going to have minus twice I, the product of these two terms. And plus I squared root 3 minus 1 squared. So let's just simplify this. First thing I note is whoever designed this question, I think they were trying to be nice because this is the difference of two squares. So I get 2i times 3 minus 1, or 2, so it's 4i, minus 4i, don't forget the minus sign. Not sure what's happening with the first and last term, but let's just expand it. So we get 3 plus 2 root 3 plus 1 minus 4i. Got to be careful here. So are we talking about this here? This number here? Yeah, so there's no extra square root. The question seems to be written fairly well. No hidden tricks. Let's see, and this other term, well, okay. You have to remember this is minus 1, so we get minus this being expanded, which is 3 minus 2 root 3 plus 1. Now it's just a question of doing algebra. There's a 3 minus 3, so that will cancel. I don't like doing cancellation inside brackets. So I'm going to be a little bit naughty and do this cancellation. So this and this, they do cancel out. This will add with the other term and a plus 1, minus 1. These will cancel out. So I will get 4 root 3 minus 4i. And because there's a common factor of 4, I think it's easier for me to write it as that. Okay, so we have our answer. So we're looking for the real part and the imaginary part. So A is going to be 4 root 3, and B is going to be minus 4. Now, I'm not sure if I should go and plug these in right now. I might hold off on doing that. So I have my answers. I might continue on to try and get the rest before I put it in. All right, so next part. It's saying find the modulus and the argument, principal argument of this number. All right, well, now that I found the number, that shouldn't be hard. So what is modulus of z squared? It's part B. It's going to be the modulus of this number. Now, I might just point out, this is going to be 4 times the modulus of this number. You don't have to do it this way, but it seems quite convenient, which is 4 times the square root of 3 plus 1, or 4 times root. 4 times root 4 is 2, it's 8. So it's a very nice number. Also want the argument. Now here I have to be careful. I could try and pull out a calculator, but I don't think that's necessary. I can draw a picture. So its real part, did I get this right? Is that the same as I got before? I feel like I did this calculation earlier. I got something different. Let me just double check my earlier working, because I don't want to get this question wrong. Oh, no, I did do it right.
Yeah, I can see right at the top. You want a plus before the I in the very first line.
Plus before the I?
Yeah, so you've transcribed Z. Oh, no, you haven't. Sorry.
No, it seems fine.
No, that's fine. The example I was looking at had a plus instead of a minus. Okay, so in that case, I think everything should be fine. Yeah.
Yeah, so they are randomized because you're seeing a different
Yeah, that's
question
right.
to what I'm seeing.
Yeah.
Yeah, so, all right. All right, so no, this is fine. So the real part is 4 root 3 and the imaginary part is minus 4. So I can draw that. We have a 4 root 3 on here. You go down minus 4. Now minus 4 is not as big. It goes down there. And well, what we're actually looking at is a very well-known triangle which has relative edge lengths 1 root 3 and 2. So I know this angle here is going to be 30 degrees. It's going to be pi over 6. So actually, remembering that the angle is measured counterclockwise from the real axis, this is principal argument. So this is z squared. So the principal argument of z squared is minus pi over 6. I think I've done that correctly. 4 root 3, 1, 2, 3, yep. All right, so what else do we need? We have our modulus, we have our principal argument, and then it says, well, use these to work out the modulus and principal argument of the original z. How do I remember those angles to radians? Well, mostly it's practice. In this case, so if you want to think in terms of degrees, because degrees are sort of more human-centric numbers, this is 30 degrees, this is 60 degrees. Well, just remember, one way to do it is this is 1/3 90 degrees, which makes it 1/3 of pi over 2. You could remember it that way, pi over 6. If you don't like that, it's actually 1/6 of 180 degrees. That's radians. Yeah, so we'll talk about entering the answer once I actually enter the answers. It's 1/6 of pi. So however you remember it, these are sort of things you should remember. I think I most remember that there's two of them. There's pi over 3 and pi over 6. Now this one is bigger because obviously you're not dividing by as much. This one corresponds to 60 degrees. This one is smaller, corresponds to 30 degrees. So that's what's going on in my head. But after a while, you just get used to it. Yeah, so Sean's right. You can also use the arctan if you have access to your calculator to do that. I mostly don't want to pick up the calculator if it's not necessary. Right, so what do we have for part C? So I want the modulus of z, and I know that the modulus of z squared is 8. So this is actually going to be the square root of the modulus of z squared, which is the square root of the modulus of z squared, which is the square root of 8. So it's just going to be root 8. Now I think root 8 is fine. So I could either enter that or I could enter 2 root 2. And I think this answer should be fine. Part, that's the principal. Yeah, that's the principal Sorry, that's the modulus. What about the argument? So we're looking for the argument of z. And there must be a hint here because we know the argument of z squared. So what's important here is that the argument of z should, well, I might write it this way. The argument of z should be the argument, sorry, it should be a half the argument of z squared, possibly up to some multiple 2k pi. So I could work out what this is. That one could be principal, actually. And then work out if I need to rotate it to make it really work. So an argument of z is going to be 1/2 of, what was it? Pi on minus pi on 6. So that's going to be minus pi on 12. And in fact, that's perfectly good. That's going to be in the range I want. And I actually think this will always work because the nice thing about the principal range is that a half of a number, yeah, actually this will always work because I don't even need this now that I think about it. Because if theta is in the principal range, if it's between minus pi and pi, then 1/2 of theta is in minus pi to pi. In fact, it's something smaller, but that's good enough. It just proves to me that I don't need to do any correction to this calculation. So this will be the answer for that. So finally, part D. Now, part D says, it has a very important word. We're trying to give you a hint here. It says hence. So that means there should be something that we've done which will lead us to this answer. So it says, hence, enter the cosine of pi over 12. So how does this all work? So note, z, well, in polar form, z is just equal to, well, it's going to be 2 root 2 e to the minus I pi over 12. Or in other words, it's going to be 2 root 2 cos pi over 12 plus I sine. Sorry, I lost the minus sign. Minus pi over 12. So if I'm reading this correctly, I can say that the cosine of minus pi over 12, or 2 root 2 times that, that's just going to be the real part of z, which is going to be root 3 plus 1, if I remember z correctly. So it's just the real part of z. Be very careful with my writing. Minus pi over 12. Okay, so that's good. So that tells me that the cosine of minus pi over 12 is equal to root 3 plus 1 over 2 root 2. That wasn't the question, though. The question was for pi over 12. Does anyone want to tell me how I can get that from that value from this value? Yeah, it's even. So this is actually all we need, because this is going to be the same as the cosine pi over 12, since cos is an even function. Now, in the exam, if this was the question in the exam, a lot of this writing is not necessary. I'm just trying to explain to you what my thought processes are. And now we can actually go and enter them into the computer. All right. Now, let's go. So we worked out, if we look at our page, I already worked out that the real part was 4 root 3. So the way to enter that, or the way I would enter that, is times the square root of 3. Please make sure to try and use the syntax advice we provide for you. In the exam, these green boxes will be there. If we think there's any syntax you might struggle with, we're going to try and put it in just to remind you the syntax you were learning through the session. Now, that was the real part, and the imaginary part should be minus 4. So these should work. I could check how did I do, but I should be confident in my answer. So the modulus we found was 8. The argument we found was minus pi over 6. So I am using capital PI for pi. If at any stage the text in the question is too small, you can always do what I'm doing and zoom in to make it easier to read. So there shouldn't be any excuse about not being able to read something. You can control the zoom level in your browser. So argument, well, that's just going to be the square root of that. This should be an acceptable answer. If you prefer to simplify it, you can write it as square root of 2, but the computer is quite smart. It doesn't need you to simplify things for it. So that answer should be fine. The argument, so that should be minus pi over 12. If you want to, you could enter it like this. That should be fine, but personally I would do that. All of these should be fine. Any valid syntax for the answer should be valid. And for this one, well, we found out it was the square root of 3 plus 1 divided by the square root of 8. Now, here's something I want to point out to you. It's tricky to enter your answers correctly, so it's good to have these preview buttons. So for a lot of the entries, except for these numerical ones, this is just a number. For things like this, you can actually click preview and it should preview your answer. And if I do that, I can see I haven't typed it correctly. So I can fix that up. That should be what I meant if I go double check. And that looks like what I want. It should sometimes also pick up syntax errors. So here it's telling me there's something wrong. I can't tell you what, but there is something wrong. But yeah, so is that what I wanted? Yep, that's what I wanted to enter. So Sean, should we check our answers or should we just accept our mistakes if we make them?
Yeah, I think go for it. But yeah, keep in mind, of course, that you can't do this when you're sitting the actual exam.
Yeah, during the exam, you have to, I mean, if you want to, in that case, it's actually better to find a way to check it without the how did I do button. This question would be quite easy because I could actually compare it to a computer. But Yeah, so far so good. All right, you want to do the next question?
Yep, sure thing. Okay. Oh, I just realized I'm sharing my app, not my screen, but that's okay. I'll just switch when I want to show the Maple TA entry part. Okay, so here's our next question in the algebra section, and this is the first that we've seen of this sort of type where we've been given a Maple output, a Maple session has kind of been reprinted for us up here, and we want to use what it tells us to somehow answer the questions that follow, right? Now, typically, when you're given a printout of a Maple session like this, it's not meant to confuse you or anything, right? It's there for your own benefit. It's probably there because there are some sort of calculations involved in answering the question that are kind of tedious or prone to error or whatever. And so the question has decided to do those calculations for you so that you don't get tripped up by sort of silly calculation errors, right? So you only have to worry, or maybe not only, but you can worry less about calculation errors and more about what the question's actually asking. So that said, I'll also say, as we've mentioned, this exam is open book, which means we said that you are allowed to have access to Maple. So if there are certain questions that you think you might be able to answer more quickly, if you are particularly proficient with Maple, you can use Maple to do that. That said, there will be no questions, or we don't expect there to be any questions that are written that can't be solved without Maple, right? And we don't really expect too many questions to be written. Like we don't expect questions to be of the form where you're significantly advantaged if you use Maple over pen and paper. As this sort of thing exemplifies where the Maple output is given to you, right? That all said, right, that doesn't mean you shouldn't know how to use Maple because, again, based on this sort of question, you can be given Maple output and you need to know exactly what's happening in each line to be able to use the information you've been given, right? So before I do anything, I might just read through this Maple output and see what's happening. So I see that this first line defines P to be some mapping from Z to some polynomial expression in Z, right? So I can think of P as a polynomial P of Z. And in fact, what do you know? The mapping Z to this thing is exactly the polynomial P of Z defined down here, right? So I know from my experience with Maple that if I write P of something, if I write P of 1, say, then I'll get this polynomial where Z is replaced by 1. Okay, so then the second line is doing exactly what I essentially implied. So it's replacing Z with 3 in the polynomial. So it's calculating P of 3. And this blue line tells me that the result is 0, right? So this is telling me that P of 3 equals 0, right? Just in case that's not super obvious. What about this third line? Well, same thing. It's substituting some value for Z and getting 0 back out. What's the value it's substituting? Well, it's this thing 3 plus 4 times capital I. We all know, hopefully by now, that capital I is what Maple uses to represent the imaginary unit, which we typically, when we're handwriting this, we use a lowercase I, right? But anyway, it's telling me that if I substitute Z is 3 plus 4i into the polynomial, I get 0 back. And what's its last expression telling me? Well, it's saying that if I substitute any value Z in to this expression, so P of minus Z minus P of Z, I get 0 back, right? Which I think looks a little bit more familiar if I rearrange it to look like this. Okay, so that's all that I can learn just straight from the Maple session. Now let's actually go ahead and see if we can answer these questions. So part A here is just well, also this is our first experience with an essay box question, right? So this is not an automatically marked question. It's not something where you enter a number or a value, and then it's a binary right or wrong answer. In this, you need to type an explanation of some sort into the box, and it will be marked by a human marker after the fact. So I need to explain something here. And what am I trying to explain? I want to explain that z minus 3 is a factor of p of z and that z plus 3 is a factor of p of z. So this might be, this might require multiple approaches. It might be a fairly hefty explanation, right? If I'm thinking about my exam technique, I might look ahead and see that there are 3 parts to this question, but I might have also noticed that this question is worth 5 points. So it's probably safe to assume that this part A is worth more than 1 point. And so I probably need to supply more than one argument, right? So that's something to you might like to be thinking about when you're answering these sorts of questions. Okay, so that said, what is my argument going to be for these 2 explanations? Well, I know a few things from the Maple output already. I probably want to use them. The most likely one that I want to use is going to be this. So what I get from the second Maple line, because it involves a 3, right? And I want to talk about perhaps at least instances what happens with z minus 3. And if I think about the different theorems I know that apply to polynomials, hopefully everyone's come up with the same idea by now, which is that I'm thinking of the factor theorem, right? So the factor theorem tells me that since p of 3 is 0, this is the same as saying that z minus 3 is a factor of p, right? So the factor theorem helps me get at least this first factor here, z minus 3. And how I know that p of 3 is 0, that comes from the Maple line that we just discussed, right? What about this second factor, z plus 3? So for that one, I might need to use some other information from the output. The third line about 3 plus 4i is not going to be useful for me yet, I don't think. But what about this fourth line from which I concluded that p of minus z is p of z for all z? What does that mean, the polynomial p? What does that tell me about the polynomial? Yeah, thanks, Hugh. It tells me it's even, right? So I'm just writing down like the ideas I'm thinking of now, and then I can convert them to a typed up explanation at the end. So I know it's even is what I'll say. So since p of z is even, then in particular, I know that p of minus 3 is going to be the same as p of 3, which I already know to be 0, right? So again, by the factor theorem, z minus minus 3, that is z plus 3, is a factor. Okay. Yeah, so a couple things to point out here. So someone mentioned in the chat conjugate roots, right? Now that is, I'm glad someone mentioned it because that is one of the most common mistakes that came up in answering this question last time. Lots of people successfully argued why z minus 3 should be a factor using the factor theorem, but then they jump straight to saying and z plus 3 will be a factor because of the conjugate root theorem, right? Why does the conjugate, so that's not correct, right? Why doesn't it work? Well, because the conjugate root theorem says if the polynomial is a real polynomial, right, which this one certainly is, right, all the coefficients are real numbers, then if z is a 0, is a root, then so is the conjugate of z, right? So we just found that 3 is a root, but the conjugate of 3 is just 3, right? I mean, to make it really clear, 3 is really 3 plus 0i, right? So the conjugate of that is going to be the conjugate of, well, it's going to be 3 minus 0i, which is still just 3. Yeah. So that doesn't tell me anything about -3 being a root or not, and that's why I can't use the conjugate root argument. But it was a common mistake, so I'm glad we get to point it out here. The other thing I just might quickly mention is we didn't. I mean, this was it was useful that the maple output told us that the polynomial was even, but we could have observed that just by looking at the polynomial as well, right? Because all the powers of z are even, and that in a polynomial, if all the powers of z are even, that's enough to it's an even function. So you could have said that as well if you didn't notice that this line here was telling you that the polynomial is even, right? And also, you don't even necessarily need to say that. You don't like the word even doesn't actually have to come up in this argument, right? Based on this line here, I can read straight off that p of -3 is going to equal p of 3, right? Without having to say it because it's even or anything. But it is nice to make that reference, I think. Okay, so we can try typing that up in a second. But let's also look at these other two parts here. So part A established two of the factors of p. Part B is talking about finding some complex roots of p of z with non-zero imaginary part, right? Which is to say, we want answers that we want roots that aren't real, right? So how can we do that? Well, again, I'm going to go up to my maple output and see what it tells me about non-real roots, right? So the first line doesn't tell me anything, of course. It's just defining p. The second and fourth line tell me, well, the second line tells me about just a real root, so that's not super useful. The third line I haven't used. It tells me about a complex root, right? A non-real root, rather. It tells me that 3 plus 4i is a root of the polynomial. So right off the bat, for part B, I know that 3 plus 4i is certainly a root, right? Are there any suggestions in the chat? What theorems or rules can I use to come up with some other roots, knowing one of them already? Yeah, great. So we mentioned the complex conjugate theorem before, right? It didn't help us for part A. It will definitely help us for part B. So by the conjugate root theorem, the conjugate at 3 plus 4i, that is 3 minus 4i, is a root. Okay. Of course, I checked that I was allowed to use the conjugate root theorem because remember, it only applies when all coefficients of p are real. Right, so that's an important thing to check before you can actually use the conjugate root theorem. But we checked already. I can scroll back up and look at it, right? All the coefficients are real numbers, so I can apply the conjugate root theorem. And so I have that 3 minus 4i is another root. Henry says he asked Maple to solve the polynomial for him. Yeah, so that is perhaps a nice example of why this sort of question might not work so well in an open book exam, right? As far as we're concerned, in terms of making interesting questions that aren't solved by typing something to Maple. Okay, so as we said, we're looking for 4. We're looking for 4 complex roots here, right? We got one for free. We got a second one via the conjugate root theorem. I need 2 more that aren't non-real. Also, Hugh asked to check what the degree of the polynomial is. It's a degree 6 polynomial. So if I can find these 4 different complex roots, along with the 2 real roots that we already found in part A, I'll have found all of them, right? Because of the fundamental theorem of algebra. Yeah, so G has written up the 2 that we're missing. Can anyone tell me, like, how might I have come with those? So for example, G is written -3 minus 4i is another root. How could I be able to tell that from what I already know about the polynomial? So I'll just scroll back up here. Yeah, exactly, Ben. So it's because I know that the polynomial, the function is even, right? Muhammad mentions something about the spacing of the roots. You need to be a little bit careful about that argument. That's true if we're talking about nth roots of something. If I'm trying to solve, say, I don't know, this, right? Then for sure, the 6 roots will be evenly spaced around a unit circle in this case, right? Or if the right-hand side is really anything, any constant value. But this is a little bit more complicated of a polynomial, so I'm not sure. I don't really know about the spacing, I guess, of the roots for this thing, unfortunately. But yeah, let's use the evenness of this polynomial, right? So since p is even, I know, for example, that p of 3 plus 4i will be the same as p of minus 3 minus 4i, right? And I know that this p of 3 plus 4i is 0 from that maple output. So that tells me that minus 3 minus 4i is a root. Okay, so there's my third one. And the fourth one I can find very similarly. I'll apply the same trick to, so I just applied that trick to, I'm running out of colors here, to this root that I'd already found, right? Well, what about this root too? Yep, so I also know that p of 3 minus 4i is 0. But because p is even, that will be the same as p of minus 3 plus 4i, right? Which gives me my fourth root. Okay. Let's make sure I'm color coding correctly. So that's the sort of argument that we're here, right? Of course, for this question, this particular question, we aren't asked to give an argument. We're just asked to find 4 roots. So I've been very careful in writing what theorems I'm using in each case. For this particular type of question where it was just asking for numbers or answers, I didn't have to perhaps be so neat in my working, but I'm doing it for your benefit for this revision session, of course. Okay, so I found 4 roots. Are they distinct? Yeah, because 2 complex numbers are only the same if both their real parts and their imaginary parts are the same, right? And that's never the case for any 2 of these 4. So I should be done here, right? And again, we can look at how we'll type that into the action box in a second. But first, let's finish off by dealing with part C as well. So this is actually pretty standard, I think, type of follow-up question, right? We found our roots. Now we want to factorize p of z. And in particular, the type of factorization we want here is one that is a product of real linear and real quadratic monic factors. So first of all, I might think, so if I had not been asked for real factors, right? If I'd just been asked to visit without any further argument, of course I could just say that p of z is z minus each of the roots I found, right? So I could just say z minus 3 plus 4i times z minus 3 minus 4i, etc., right? For all 6 of the roots I found. Unfortunately, that's not quite what we've been asked for, because we want to factor it into Yule factors in particular. So this is a real factor, right? So that's fine, and so is this, which is to say none of the coefficients are non-real, right? But I'm running into trouble, for example, with this term here. This has, the constant term is not real, so the factor itself is not real, is not a real polynomial, right? So I need to use the trick that we discussed in lectures about creating a real quadratic factor from 2 non-real linear factors, right? And you might remember the trick there is to pair up roots with their conjugates. Okay, so I might just say, recall, because this is a trick we've seen in lectures, so hopefully you remember it, or in an open book exam case, we actually just bring it up. So we can call that if alpha, say, is a root, then if I look at z minus alpha and z minus the conjugate of alpha, then this happens to expand out quite nicely. So I get z squared. So actually, so you might remember that it's just z squared minus 2 times the real part of z of alpha times z plus the length of alpha squared, right? So you may have just committed that to memory or just sort of learned osmosis by doing these sorts of questions a lot. If you don't remember, we can just expand it out, right? So this is really z minus alpha plus alpha bar z, and then it's plus alpha times alpha bar. So I could also get here by just remembering that complex number plus its conjugate is twice its real value, and complex number times its conjugate is its length, or its modulus rather, squared, right? At any rate, now that I know that greatly, because I can say, so yeah, so I might just, so I'll expand the two pairs of complex conjugates I found. So z minus 3 plus 4i times z minus 3 minus 4i. Now, if I didn't remember this trick, by the way, that I've just written up, I could just blindly expand this out. It might be a little bit, but it would all sort itself out in the end. But since I remember the trick, I'll just apply it. So it's going to be z squared minus 2 times the real part of this root, so 6 alpha, 6 z, and then plus the length of this root squared. Sorry, the modulus of this root squared, right? So that would just be 3 squared plus 4 squared. So in this case, it's just plus 25. Okay. And a completely similar approach will work for the other two roots. So that's minus plus 4i and minus 3 minus 4i. Right. And so what happens here, same idea. I'll get z squared minus 2 times the real part. The real part is minus 3, so this is actually going to be a plus 6 in the end, z. And then again, I'm just adding modulus squared, which is still 25. It's still 9 plus 16, right? Okay, so I'm trying to keep track of my color coding. So this is a real quadratic root, right? And so is this, because now all my coefficients are real values. And so I've accounted for all possible 6 roots, so I should be done. So just to finish it off, I can write out that this polynomial is z minus 3 times z plus 3 times these two quadratics that we found. So times z squared minus 6z plus 25, and then again times z squared plus 6z plus 25. Okay. And maybe I can just check that I've satisfied the conditions. So I have 2 real linear terms. That's z minus 3 and z plus 3. And I have 2 real quadratic modic factors, right? Because this is quadratic for sure. It's a real because the coefficients are real. And it's modic because the coefficient of it is 1. Okay. All right. Okay. So that's the situation. We've answered all 3 parts. How might we type it up in Maple quickly? So bear with me while I change how I'm sharing my screen so that I can show that. I think so I'm showing my screen, I think. Yeah. So so how am I going to answer this in Maple TA? Well, so first of all, my argument for why z minus 3 and z plus 3 are factors, and this is just something I want to type up, right? Like we mentioned at the start, you don't need to worry too much about formality or aesthetics or anything, right? Just get down all the important things that you need to get down. So here, I surely want to mention that I'm using the factor theorem, right? So by the factor theorem, since p of 3 is 0, z minus 3 is a factor, right? I don't think it would be necessary here, but maybe I could say here p of 3 is 0 from the, I think it was the second line. Right? So something like that would be a model answer. You don't need to be so grammatically correct in everything, so long as you're getting the important points down in an understandable manner, that's sufficient, right? I also want to explain 3 being a factor, so I could say something like from the 4th line of Maple output, We know P of minus Z equals P of Z. So P of minus 3 equals P of 3, which we already know to be 0. So again, by the factor theorem, Z minus 3, which is Z plus 3, is a factor. Okay, so something like this would be
Zoom in a
sufficient.
little bit.
Oh yeah, sorry, yeah,
Okay.
thanks, Josh.
A little bit hard to read, that's all. I could do that too, yeah.
Yeah, I was just thinking, yeah. Well, I could do a combination actually. How about something like that? So, whoops. So something like this would be sufficient. This is probably more than sufficient, really. But I wanted to make sure that I was getting my point across properly. So that's what I decided to type up. Right. I noticed I didn't use the equation editor or anything. If I really wanted, I could have for writing things like P of 3 is 0. But it's not necessary, and it's a bit of a time waster, so I'm not bothering. Okay. All right, for parts B and C, these are correctly marked questions, right? They're not essay box type, so I need to make sure that I'm writing things correctly, like using the correct maple notation. So for part B, I want to write in my 4 roots. I can kind of see them behind me, behind the window there. I see the first one, but I can remember that. So I remember that one of them is 3 plus 4i, right? So I'm thinking 3 plus 4i, but I'm not writing it like this. I'm writing it like this. And very conveniently, I've been reminded, right? If things are being multiplied, I must use that asterisk. So I don't write 4i, I write 4 star i, 4 times i, right? And when I'm talking about the imaginary unit in Maple, I always use capital I, which is what that is there. It looks like an L, but that's because I don't have serifs in this font, I guess. So that's a capital I, right? I want to enter 4 roots here. And so this is a little bit of a different entry form again, because typically I just write a number in these boxes. But here I've been asked for 4 different answers, so I should check how I should do that. It's mentioned here, right? Enter your roots in the box separated by commas, right? So my 4 roots, I'll just separate them by commas. So where they, I've also got 3 minus 4 times I. I've got minus 3 minus 4 times I. And I've got minus 3 plus 4 times I. Okay, something like that. Question asks, should I write by the factor theorem? I would definitely be name dropping the factor theorem because this question, part A, is asking for me to explain something, right? A marker is going to be looking through this and looking for me to have mentioned certain things to get the marks, right? So I want my explanation to be as clear as possible. So I mentioned that I'm using the factor theorem. He asked to be mentioned that's even. So I didn't mention it here, right? Because I could use the maple output as I mentioned. So the maple output, when I replaced Z with 3, was enough for me to get the answer right. You don't need to do it that way. You could have said since P of minus Z equals P of Z for all Z, P is an even function. So if P is a root, then so is my C, or something like that if you wanted. I think that also would be sufficient. But you would want to be name dropping the important thing. So here, it's important that I recognize that it's even, right? Here, it's important that I'm using the factor theorem. Or here, it's important that I'm using this property, I guess, right? Cool. Okay. All right. Okay. And finally, part C. So I want to write the factorization of P of Z, which I've written down here. So maybe I can shrink my screen a bit so I can copy it straight over. Yeah, okay. So what I want to write here, I want to write Z minus 3 times Z plus 3. So I'm going to be careful and use asterisks every time something is multiplied. Also in here, so this is 6 times Z, right? Plus 25, and then it's all times Z squared plus 6 times Z plus 25. So in my head, when I'm typing these things out, every time I think this is something times something, I say the times out loud in my head so that I remember to write the asterisk here, right? As Josh mentioned, it can always be a good idea to use the preview button here. This looks pretty much like what I wanted. For this example, it's probably not as useful because a polynomial. Polynomials usually do look like what they're supposed to. But again, if you wanted to check, you can do this sort of thing to check, right? And I think that's about all I have to say about this question. I think you might notice if you've been testing for this particular question, I think the marking, the automatic marking is written in such a way that it actually does accept if you leave out asterisks, and that's not always going to be the case. Never assume that it will, is what I would say there. And I guess again, we can cross our fingers and hope that yeah, these are marked correct. And notice that this essay box question, it's yellow, right? It's not red, which means it's not wrong, but it's not green, which means it's not considered right yet either. I have to wait for, I mean, in the behind the scenes, what's happening is what a human marker is going to come through and give this a grade later, right? I think that's all I have to say about this. Any comments or questions, Josh?
Yeah, so try to get the syntax right. We'll do our best to try and put in things to recover if there are obvious mistakes we can predict, but don't rely on that happening. It's better if you just get it right the first time.
Yeah, exactly. Yeah, I mean, I also mentioned, don't think it's the end of the world if you finish the exam and then realize you forgot an asterisk somewhere or something, right? Typically,
we also plan to look at all the things marked wrong to make sure that they really should be marked wrong.
Yeah, exactly. Yeah, so it is possible for the human markers to overwrite something. Like if I am going through someone's solutions and I see that they left out that star there, but otherwise it's clearly correct, but the markers said it's wrong, then I can overwrite it and say, actually mark it correct, because the student knew what they were doing and they pretty much showed how to type it out and everything like that.
Yeah,
At the same time,
I'm hoping I can pre-program a lot of these decisions into the code.
Yes, yeah.
But we can't catch everything, but we'll do our best.
Yeah, so you do have that safety net, but don't rely on it.
Right, I'll go on with my question, shall I?
Sure.
Okay, so it's another Maple question. So it starts with giving you a lot of calculations. I mean, we don't want you to spend too much time having to do calculations, even if you did have Maple at your fingertips. That's not really the point. Computers can do calculations, you need to do thinking. So we have information, and now whenever you see the Maple output, it really is the first thing you should read. You should be looking at it, trying to work out what is it telling me? Why is it here? That might not become clear until you actually do work through the question a little bit. Let's just try and work out what it's saying. So they're just defining some matrix. If I look in the question, okay, this matrix is the same as the matrix they're calling A, no tricks there. They're defining a vector called A, lowercase a, matching this lowercase a vector. All right, then this next part is a calculation, and it's not quite clear what it says straight away. So they're saying we're looking at A times the vector A, and it's done the calculation. What I need to notice is actually that this vector -1, 2, -7 is the same as B. So it's not told to me, not quite explicitly, but it is there. I have the fact A times A is equal to the vector B. What else do we have? Again, another vector V, which is defined in the code, also called V. And then we have A times V is very interesting. I have A times V is equal to the vector 0. So pretty much that's the only two things this code seems to tell me. It defines all these things and does two calculations. I need to make two observations about these calculations. So how is that helpful? I'm just going to keep these facts here. All right, now it's saying, okay, first thing's just a multiple choice question, a multiple choice with multiple answers. So it says select all the answers that apply. Now, we want to find all solutions to this, all vectors x, such that ax equals b. Now, what do we have? So first thing it suggests, well, let's just see what we have. It suggests v. Now, is that? Looking at this, av, I guess I'll do it over here. What do I know? I know that a times v is 0, and the vector b is not 0. So this is a no. How do I mark this? I guess I'll do no. What about 0? Is a times 0 equal to b? Well, that one I don't have to do any calculations. A times 0 is just 0. That's definitely not b, okay. V plus 7a. Now this one's interesting, because what do we have? We have a times v plus 7a. Now the wonderful thing about matrix algebra is it's the sort of algebra you're used to. You can distribute over a product. So this is a times 7a. And actually, the nice thing about scalars is they do commute with the matrices. So this is AV plus 7AA. And here's where these facts come important, because AV again is 0. We've seen that twice. We've seen it already. And this is 7 times B. Now, 7 times B is not equal to B most of the time, especially not here. Maybe someone can post a situation where 7 times b would be equal to b, but not here. It doesn't work here. So this one's no, because this is 7b. That's not b. So this is a no. What about a? What about a times a? Well, a times a is equal to b. That was the Maple code. So this is a yes. That one's yes. I'll put a tick in the box. A times b. Well, they never calculated a times b. Does anyone want to tell me a times b? Should I start doing the calculations? So some people want me to do the calculations. Some people say no. So why not? Yeah, it's the matrix shape doesn't work. A is a 3 by 4, and B, so you get a 3 by 4 and a 3 by 1. These are not compatible. This thing's not defined. So there's no possible way it could be a solution. So this is a no without looking. This is also no, because I can't do this calculation. I can't add v and b. I can't add v and b. 8 times v. Well, this one, the calculation's possible. So a times 8v. As I mentioned, this is the same as 8av, but we were told that this is 0. So this is 8 lots of the 0 vector, which is the 0 vector. So this is a no, it can't be equal to b. A plus 7 times v. Now this one's tricky. I think I have to do the calculation. So we get a times a plus 7v. By now you should be used to what I'm doing. It's a lots of that and 7 lots of this, which is b, by what we knew, and 7 lots of 0, which is b. So this is a yes. And 8 lots of a, well no, that will give me 8 lots of b, and 8 lots of b is wrong. So a, 8, a, that's right, is equal to 8 lots of a is equal to 8 lots b. That is not equal to b. So my final answer is there's actually only 4 on this. There's actually, that is right, a plus 7, and the rest are wrong, I believe. Yeah, so there's only 2 there that are really yeah, there's only 2 there that would work. Someone says A would need to be the identity matrix. Not sure I understand why.
Yeah, he's referring to just the case where you were considering when x equals b.
Would it have to be the identity matrix, I wonder? It depends on B, it depends on A. I mean, yeah, I'm not convinced by that argument, because a special B and a special A might get this to work, like eigenvectors. Oh, wait, sorry, we don't know that till next year. But yeah, that's not necessarily true. Okay. Now, in the box below, it says, state whether this equation has an infinite number of solutions and justify your answer. So there must be something about what they've told us which we can use, because I don't think they want us to do any row reductions. They haven't done any row reductions for us. Okay, so I think I see something which works. Actually, this is something Sean did mention in his lectures, that when you're solving AX equals B, there are different types of solutions. So I might just remind you of that little fact before we move on. When you're solving this, there are three things that can happen. You can have no solutions. You can have unique solutions. So that means exactly one solution. And then actually it suddenly jumps up to infinitely many. There's no room between infinity and one. Like, it just jumps all the way up to infinitely many. Now, what do we know so far? This is not true, because I had A times B, A times A is equal to B. I had a solution. So there is more than one solution. Is this possible? Well, I had A times A is equal to B, and I had A times A. I mean, the question even gave me an example, A plus 7 B is equal to B. It gave me two solutions. That means it can't be unique. That actually means that there's only one choice left. There has to be infinitely many. And if you're clever, you might actually even notice the following. This is equal to B for all T. So I'm wondering what I'm going to enter here. Let's go to the actual question. All right, so we've done the calculations. What have we worked out? It was A and that one. Those are the only two. And now I have to explain whether or not this has infinitely many solutions. So what shall I say? The solutions, I should zoom in, take my own advice. So solutions to equations of the form A, maybe just to make it a bit clear, I'm going to say matrix AX equals B have either, now because I can list things, I might just use a list. They can have either unique solutions, sorry, no solutions, unique solutions, infinitely many solutions. Since both A and A plus 7V, sorry, 7V are solutions, and I suppose to be very precise, these are different, is not equal to this must have infinitely many solutions. like the font change. And don't worry so much about typos. We can read them as well. I'm sure I've made typos in typing this up. This must have. So I think that would be a fine answer based on what we taught you. Any comments on this, Sean, as the algebra lecturer?
Well, yeah, I mean, just I'm being picky here. One typo you have in the brackets is you want a something equal to a plus 7v, right? I only point that out because I might mention that it's not the sort of, even that is not the sort of typo that I think would lose a marks for that explanation. It's pretty clear to me that that's a typo because you've already typed a plus 7v before. So I don't think even that would be penalized, but keep an eye out, of course.
Well, it says 3 points. Now, in practice, it shouldn't take you as long as I did it because I was very explicitly going through all the calculations. Half of these things can't be calculated, and the rest are very simple based on what we told you. Now, there are more ways to do this. Actually, I prefer my second solution, just pointing out you can actually construct them a plus t times v. But this is a good way to do it. It really shows you understand what was going on.
Yeah, I'd also point out that this answer is almost certainly the intended answer based on the way the question was set up. But based on the actual student responses, most students actually missed this way of answering it. So actually, the majority of students solved this one by row reducing the matrix A, which of course is unnecessary based on what we've just seen from Josh's solution. But it is another way around it. It's much more time consuming, right? And it's a lot harder to write up your explanation. So if you did it that way, it was a lot harder to get the full marks for this part. But I'll point out it's another valid method, but not the one I'd recommend.
Yeah, I mean, the other one is just to actually do, let's see,
I think you want V, not B again. Yeah.
Yep, it happened again. I realized. Be very careful with what I'm saying. Is equal to A times. I put a dot for multiplication. Shouldn't really need to, but. So I mean, that would also be a valid answer, just a more constructive one, because you can actually see you can see a whole line of solutions.
Yeah, I like that argument. One other thing I was just thinking to point out is, notice we haven't bothered making all the vectors bold here, right? That's something that we were very particular about making sure you did in your assignments. But again, we don't expect perfect presentation in your answers for this exam, since it's time sensitive and all that. So yeah, it's absolutely fine to just type the letter A. You don't have to, or X or whatever. You don't need to bold those things.
You don't even really need the multiplication sign. I'm just putting it in there to try and be clear.
Yeah.
But yeah, this would be a perfectly good answer. Anyone who did this really understood what's going on. All right, so I'll let you, I guess I might just check my answer before I move on. What did I do? Yep, so there are only 2 that were correct there. And this will be marked by somebody else. All right, yeah, your turn.
Yep, cool, okay. So I think this should be a bit of a quick one. I didn't tab fast enough. Okay, there we go. Okay, so this is a question about vector geometry, it looks like. And so it seems pretty likely that I am going to be drawing up a bunch of diagrams to answer these problems. So there's a setup that A, B, and C are non-collinear points in R3. M is a midpoint of AB. Those are all probably useful things for me to know. I also have this thing about P being a point satisfying some condition, right? Which I'll come back to later. But as I look ahead in this problem, I can see that I actually don't talk about the point P until part C. So I won't worry too much about this important looking equation just yet. So let's just start by looking at part A. It's asking us to find CM in terms of CA and CB. Remembering that M is the midpoint of AB, and A, B, and C are three non-collinear points. Well, at this point, I hardly give anything to do but try to draw up a diagram and see what's going on here, right? So I have 3 points A, B, and C floating out in three-dimensional space somewhere, but I can't really draw in three-dimensional space, so I'll just think about the plane going through those 3 points. They're non-collinear, so I can draw them in sort of some triangle shape. And I also have this point M, which I know is the midpoint of A and B. So if I imagine the line from A to B, then I know that M is halfway between A and B on that line. Okay. What else do I have here? So for part A, I want to talk about CM. So I may as well draw in that vector. And I want to write it in terms of 2 other vectors, CA and CB. Okay, so I've drawn all those in to let me kind of have a good idea of what I probably should and shouldn't use. And finally, I want to actually attempt this thing, right? At the moment, I want to find CM in terms of other things. So I'd like something else. I'd like to use some other property of M that I already know. And really the only thing I know about M is that it's the midpoint of the interval AB. So in terms of vectors, what does that tell me? Well, I can put in, for example, this vector here, AM, right? And I know that it has the property, well, what in particular do I know about it? I know that AM is half the length of AB, right? And of course, it's the same direction. So I could say that the vector AM is half the vector AB. Yeah. So that seems useful. From here, I might be, I might get here via various methods, right? By playing around with different vectors and that sort of thing. But the way I think about this problem from here is to say I want to write CM in terms of CA and CB. Well, now I know something about AM, so maybe I'll write CM using the triangle addition law. I can see that CM is just the vector CA plus the vector AM, right? And like I said, I have a way of expressing AM in terms of A and B. So CA, sorry, this is the same as CA plus half the vector AB. Okay, I'm kind of getting there, right? So remember, I want to write CM in terms of CA and CB. I have a CA term, but my other term is AB, not CB. But can I bring C back into this expression involving A and B? Well, yeah, if I look again at my diagram, maybe I'll just redraw it smaller over here. So this is A, B, and C. Then AB, by various laws, you can think of it as the difference of 2 vectors, right? It's going to be CB minus CA, right? How do I remember the order there? Well, the way I remember it is CB is pointing to B, just B is. So I don't want to change the direction of CB. CA is not pointing towards B. It's I would prefer it to be going this way. So I can think of AB as AC plus CB, or I can think of it as minus AC. I can think of it as AC as minus CA. So I can think of it as AC plus CB or minus CA plus CB, right? Okay, so and now I'm pretty much done, right? I have something that's in terms of CA and CB only. I just want to clean it up a bit. So I have a CA here, and then I have a minus half of CA here. So I'm left with just the other half, CA. Okay, and at this point I'm done because I have CM in terms of something times CA plus something times CB, where those 2 somethings are both 1/2. Okay. And I believe we actually did, I think we saw exactly this proof really early in the term, like in the first or second week when we were talking about vector geometry. So you might even remember a proof like this from earlier. But that's pretty much all I think I have to say about this first part. For now, anyway. So for B, then, this seems like a pretty straightforward question. It's asking me that it's saying D is some point, such that CD is CA plus CB, and it wants to know what is the shape ACBD. So, well, I already have my diagram up here, but I might redraw it. So I have my points A, B, and C that aren't collinear. Again, I care about the vectors CA and CB here. But now also I'm thinking about the point D where CD is the sum of CA and CB. So this is a pretty straightforward question, I think. It's saying what does it look like when I add the vectors CB and CA? Well, I could think of it using my triangle law or my, I think I prefer in this case to use the parallelogram law. It's going to be the diagonal of the quadrilateral that has sides, of the parallelogram that has sides AC and BC, right? So if I imagine sort of this parallelogram here. Apologies for the shaky writing there. Then the sum of those two vectors will be that diagonal, which tells me that D must lie here. Right? Essentially, the parallelogram law tells me where D is, and even better, it tells me what the shape ACBD, right? So ACBD. It tells me what that shape is, right? It's in the name. It is a parallelogram. Okay. So that's all I think I really need there to answer that question. And by the way, if you were thinking ahead with this question in terms of exam technique, or even if you just because you're very familiar with geometry of quadrilaterals, you might remember that the diagonals of a parallelogram bisect each other, right? So if I'm thinking about this parallelogram here and the two diagonals that are bisecting, that's got to be where the point M is, right? And so, and not only are these two sides the same length, but so are these two. So I can actually quite quickly see that CM is half of CD, right? Which is, as we just saw, CA plus CB. So if you were attempting these questions in a different order for some reason, maybe you thought part B was easier or whatever, it might even have helped you in this case. Okay, so that all said, let's actually get to part C, which looks like it might be the big part, right? The tricky part. And finally, we're talking about this point P, so we care about this setup here. So P is the point that satisfies this rule, right? Well, it's any point that satisfies this rule. And part C is saying find all points P that satisfy that rule, right? So what is the rule? It's telling me that CA plus CB, the cross product of that vector with the vector CP is always the vector 0. So let me take a screenshot of that actually, so that I can refer to it without scrolling up and down again. So what can I say about this expression? Well, first of all, as we just did in part B, we just said that CD is CA plus CB, right? This term here. So since we've placed where D is now, we may as well use it to our advantage, right? So this left-hand side is the same as saying CD cross CP is the 0 vector. Okay, so how does that help me anyway? So I have that the cross product of two vectors is the 0 vector. I think it makes sense to think about this geometrically since I'm talking about a set of points that satisfy something. So what is the geometric interpretation of the cross product? Well, it tells me two things, right? I know that the cross product of two vectors is a vector that's perpendicular to both of them, which doesn't seem particularly useful here, but we'll see. But I also know the length of that vector will be related to the lengths of the other two vectors, right? So I remember that in general, the length of u cross v is the length of u times the length of v times sine theta, where theta is the smaller angle between the two, right? So if in particular, so in this case, if I'm taking the lengths of both sides, I'm saying that the length of CD times the length of CP times sine of theta, where theta is the angle between those two, needs to be the length of the zero vector, which is just 0, right? And of course, this can only be true if any of these three terms is 0. So if CD is 0, if CP is 0, or if sine theta is 0. Okay, so can any of these happen? Well, CD will never be 0 because A, B, and C are not collinear, which means that when I draw out the parallelogram, CA plus CB, to find D, it's not going to be degenerate, right? So D is going to be a different point from C. What about, can CP ever be 0? Well, yes, because remember P is varying. So P can be, I'm thinking of all points in the plane. For which points in the plane is this true? Well, if P is point C, then this term will be 0, right? So I know that P, well, maybe it's a bit funny to write like this, but I guess I could say P equals C, right, is a solution, right? As in, if P is taking the value that is the point C, then the left-hand side is 0, and so the equation is satisfied. And that's the only time that this middle term, the length of CP, will be 0. So otherwise, really, otherwise, we're really just solving sine theta equals 0, right? And this is, of course, true if theta is 0, right? Or pi, but since we're talking about, well, yeah, let's say or pi, 0 or pi. But really, what I want to get at is that this is the same as saying that the two vectors are parallel. Right? Because either they have the same direction or opposite direction. Oh yeah, sure, Henry. Yeah, I mean, since P and C are points, it's fine for me to write P equals C. But if you prefer to think in terms of vectors, you could think of it as OP equals OC. Sure. Okay. So what's my conclusion here? Basically, P is the point C, or the vectors CD and CP are parallel, right? And you might, in fact, remember, I think we said in lectures that very point, right? We said for non-zero U and V, if the cross product of U and V is 0, then that's the same as saying that the two vectors are parallel. Okay, because since we're talking about a cross product, I'm assuming they're in three-dimensional space, right? So you could also just use that fact if you knew it, or you could derive it as I just did. Okay, but either way, my conclusion is that, again, I'll just draw it up one more time. Here are my points A, B, and C, and the point D is interesting to me now, and I care about the vector CD, and I care about, so actually, A and B are no longer interesting to me, actually, but I also care about points P. So where can I place P so that CP is parallel to CD is the question. And yeah, Henry's said exactly what I wanted to hear, which is that, so actually we could even, let me continue this chain here. So I'm saying that the vector CD is parallel to the vector CP, but we've seen that to prove that the 3 points are collinear, we can show that any two vectors between pairs of those points are parallel, right? So this is the same as saying C, D, and, well, CP and D are collinear, right? Because that C is common. The C is on the left and the right of that parallel sign. So that makes it even easier, I think, to see what's going on here. If I want to, if I'm looking for a point P that will work, it needs to lie on, on the line through CD. Why is OneNote restarting? Okay, we didn't lose anything. That's okay. So a P, for example, so we already said that P, if P is at C, then that will work, right? And that is on my line anyway. If P is here, say, of course, CP is parallel to CD, so that's fine. If P is over here, right? So somewhere on this extended line through C and D, then yes, the vector CP is still parallel to the vector CD, etc. Right? So it looks like my answer is the locus of P, right, or possible P, is the line through C and D. Yep. Okay. So it's probably not even worth. I'll just very quickly go through how I would answer these questions, right? So we said that our scalar multiples here are. We said that both alpha and beta are a half in this question, right? So I'll just write 1/2 and 1/2. I will point out, since it's semi-relevant, that it's always better to write 1/2 than it is to write, say, 0.5 in these sorts of questions. Maybe not for this particular question, right? But because of the way that Maple calculates things, in general, it's safer to give a fraction than a decimal. You can help it, right? In this case, I don't think you'd be, yeah, I think you'd run into trouble either way. But I'm just mentioning that I always opt for fractions over decimals if I can help it. What's my answer to part B? It is that the shape is a parallelogram. That's all I need to say here. And what about part C? So I have a bunch of options here, and I have to choose exactly one in this case. And I want the line that goes through C and D, right? Does anything here say that in particular? Well, nothing says the line through C and D explicitly, right? But hopefully I can kind of interpret each of these and come up with the correct expression. So this first one here says a line through M parallel to CD. Well, let me have a look back at my, well, let me finish off my diagram, right? Where is M? Well, I remember that M is the point of AB. And I also remember that ABCD is a parallelogram. So that M is also the midpoint of CD, right? Or I can just remember that CM is half CD, right? So in particular, M is on the line through C and D. It's one of the points P that satisfies this property. So the line through M, right, that's parallel to CD, there's only one of those, and it is exactly the line we're talking about. It is the line through C and D, right? So actually, the first option here turned out to be the one I wanted. I mean, that's good enough. I know that I only need to select one correct answer here, so that would be sufficient. I could, if I wanted, run through here and check that all the other ones don't work, right? So for example, it's certainly not a circle, right? So I can knock out anything that starts with a circle, right? So the line through C, perpendicular to AB, I'll come back to that one. The line through C parallel to AB is clearly wrong, right? Because that, if it's through C but parallel to AB, it's something like this. It's certainly not the line I'm looking for. What else did we have? The line through M, perpendicular to CD. Well, that's also certainly not what I want, right? If it's perpendicular to CD, then it's not what I'm looking for. The last one that I might be thinking about is the line through perpendicular to AB, right? So what would that look like? Well, it's through M, it's perpendicular to AB, so it's going to look something like this, I think, based on my fairly rough diagram. It's not the line through C and D, but it could be close depending on how accurate my diagram is or isn't. So I might be considering that as a potential correct answer. But between the two options, through C perpendicular to AB and through M parallel to CD, which I know to be correct, I'm going to go for the one that's certainly correct, right? If you like, you can go through the effort of showing that in general, the line perpendicular to AB is not the line through C and D, is not the other diagonal, right? In fact, you might even know that for a quadrilateral, if its diagonals are perpendicular, it must be a rhombus, right? In fact, I think we might have proved that in lectures as well. But that's the sort of approach that I would be taking here. Henry's asking for a summary of the dot product and the cross product. Yeah, so, well, just like we just saw, U cross V if u equals v is 0, then so we need that they aren't 0 themselves, right? But if the cross product is 0, that tells me that they're parallel, which is nice to know, right? The more commonly used expression, I guess because the dot product works for any vectors, not just three-dimensional ones, which you might remember, is that if the dot product of two vectors is the scalar 0, then u and v are orthogonal, right? And this is the same as saying well, it's almost the same as saying that if u and v are non-zero and u dot v is 0, then u and v are perpendicular. Okay. So those are the most convenient geometric properties to know about the cross product and the dot product. And then I guess the other thing I would remember is both these properties really come from the fact that the length of u cross v is the length of u times the length of v times sine theta, where theta is a small angle between them, and u dot v is the length of u times the length of v times cos of theta, where theta is a small angle between them. Cool. Okay. So there's just one. Oh yeah. So again, I can say, how did I do? Just check that these are all correct. I also just wanted to quickly point out something I discovered, which is kind of cool, is that it seems that there's some inbuilt spell checker or something with this kind of thing. Because if I forgot maybe I forgot where the double L's go or something in parallelogram, right? They still got automatically marked correct, as it turns out. And I think like I tried butchering the spelling of this quite a lot, and it still was marked correct, which is kind of great. But of course, it's not going to mark it's not going to mark rhombus as correct, for example, right? But I'm just demonstrating there is a spell checker. Don't get too stressed if you think if you don't remember how to spell a particular word, because it's quite likely that it will still be marked correct if you make a typo. Cool. I think that's all there is to say about that question. Josh, did you want to move on to the next one?
Oops. Is that the right one? No. Okay. Now this is another. I think we're going to go until we're done with these questions. So there are two more questions after this one. This one's actually surprisingly fast, despite the way it looks. So we have a system of linear equations, which we want to solve. Now, it's a complicated system, and the person who wrote this question is trying to be nice to us. They've given us all this maple output. And at first glance, you might think this person doesn't know how to use maple because they've done all these row operations. Perhaps this person has forgotten that maple does have a Gaussian elimination rule, which would do all the row operations for you. So if you're looking at this, you might be thinking, okay, well, there's this row operation. I want to look at this matrix here. Let's read the question. Thankfully, the person who wrote this, well, let's see. So question asks, for which value does this not have any solutions? Now, if I was working on this, first thing I'd probably notice is this thing here. This is going to be problematic in a certain case. So if you're looking at this, you might notice that this will be 0 when m is equal to, so this is 0, when m is equal to minus 7 thirds. And this thing here is actually not so bad. It looks like it's m. Oh wait, does that have a nice factorization? Oh, actually, that's even nicer than I thought. It's m minus 1 squared plus 4, I believe. So this thing is always positive. It's always strictly greater than 0. So there will be a problem here. I don't need to actually substitute in this value to work out what's going on. That thing is not going to be 0. So in this case, there's definitely going to be a problem. There's not going to be any solutions when m is equal to minus 7/3. Now there's this big box of text which is telling you how to enter your answers. At the moment, I have my answer is a single number. Enter the single number and do not use a decimal approximation. So I'm just going to, for now, put it in here, minus 7/3, and then move on with the question. And here's where something interesting happens. The solution has infinitely many solutions when m equals 2. And then it asks you to give one other value where it has infinitely many solutions. Now, that doesn't seem right if you're looking at this. If you're looking at this and thinking, what happens when m equals 2, that seems to have a unique solution. Well, it turns out you really do need to pay attention to what was going on in the row reduction. So let's step through it a little bit slowly. Step 1, we define the matrix A. This is the matrix of coefficients. You can verify this is the same checking the text. We verify the column B. This is the augmented column. And then we make A is m times B. Nothing really surprising here. We've made an augmented matrix. Okay, so that's what I would do if I was trying to solve this by hand. Step 1, we swap the two rows. That's all perfectly legitimate. Nothing wrong with that. What does this mean? Can anyone translate what this means? So row operation 2, 1 minus m. Oops, sorry, I lost the screen. Does anyone know what this row operation means? Times row 1 by minus m. Not quite. That would be, I think, the row operation. And add 2. So yeah, I think you're right. Row 2, I think this is row 2 plus minus m times row. Yes, I think it's literally just saying row 2 equal to row 2 minus m times row 1. That's all perfectly good. You're allowed to do that. Next one, it says row 3 is going to be row 3 minus 3 times row 1. Yep, that's good. That's what I would do. And then we get this matrix here, which they're showing us. And then they go on to do other things. Now, here's where you have to be careful, because this row operation, it says I'm taking row 3 and I'm making it 1 over 3m minus 1 row 3. And this next one I'll also translate. It says row 2 is going to be it's going to be 1 over 2 minus m times row 2. So this is where you have to think critically. What could go wrong with these row operations? I mean, what's the problem when you divide by something? There's a big problem we always try to avoid when we divide by something. Yeah, we can't have division by 0. So everything, that's kind of a critical thing. Everything below here has a certain assumption. This assumes that m was not equal to 2 and that m was not equal to 1/3. So that tells you actually, if you want to think about these values, then nothing below here is relevant to that thought, because it all assumes something different. Yeah, so 0 strikes again. Okay, so we were actually told this is why we didn't pick this information up from M7. We had to look at M3. Now you can look at M3 and plug in 2, but that's not really the point. What I'm really interested in is what's happening at a third. Verify, I think this is the other value we want. I think it has to be. So let's just plug that in to double check. If m was equal to 1/3, then this matrix we called M3, what is it going to be? It's going to be 1. I'm only going to actually fill in the relevant things. This will be 4 minus a ninth, so that's 36 ninths minus a ninth, it's 35 ninth. It's not 0. This is a 0. A third of 9 is 3, so 3 minus 3 is 0. This becomes 3 times a ninth is a third, minus a third is 0. And to be honest, I actually don't care what the rest is. That's a number, that's a number, that's a number, that's a number, that's a number. All I really care is verifying that this is leading, and this row doesn't cause any problems. So non-leading column. What do we conclude when we see this? Infinitely many solutions, and you could probably even be a bit more precise. How many parameters will there be? Yeah. Now, the reason I'm trying to stress these thoughts is even though this question doesn't ask for that thought, it's useful to have because maybe another question will. All right, so to this question, we were told that m equals 2 was special, and we've also found that m equals 1 over 3 was special. And then finally, the question is, for what real values of m, if any, does the system have a unique solution? All right, so this is where I go back to the working out, and everything was fine now. As long as m was not 2, as long as m was not a third, this row reduction was perfectly valid. So yeah, we only so really it just comes down to looking at this matrix and saying, when are these leading? Well, they're going to be leading as long as it was none of those other cases. So not this, not the 2, not the third. So, and here's where we do need this helpful syntax. We have all real numbers except for 2 or more. So we have this case here, and they say enter not that set of numbers. Now the syntax is not that bad, so let's just use it. Unfortunately, I believe the preview won't work here. If you do the preview, it won't show you what you've entered. We didn't program that in. So not 2, not a third, and not 7 thirds. Is that 7 thirds or minus 7? Minus 7 thirds. Just move that where I can see it. So that would be my answer. All right, now part D says, okay, there are infinitely many solutions. For m equals 2, there are infinitely many solutions. Try and find them, actually give a parametrized answer. Now, I can't do this. This one will just take some calculations, so I'll need to take a screenshot. Come on, computer. Yeah. So I can use this matrix here. So for m equals 2, what do we have? Well, it's 1, 2, 1. Here I do need everything. Minus 4, 0. This is 4 squared minus 4 is 0. 2 minus 2 is 0. This is also 0. I get a 0. I get a 1 minus 6 is minus 5. I get a, see, it's going to be 18 minus 3 is 15. And what is this one? Actually, 3m squared minus m is the same as 3m minus 1 times m. For m equals 2, that is a bit faster, Blaine, please. 5 times 2 is 10. It's 10. Okay. I didn't get 46. Yeah, you'll have to do that part properly, otherwise you won't get the right answer. All right. I might. Yeah, well, I don't really need to because I can sort of see the row reduction from here, but if we do it, I'm going to be very, very naughty and do something that I've always told students not to do. I'm just going to write down the result without telling you how I did it. This is 1 minus 3 and minus 2. So very naughty, but no one's marking my work. As long as I get it correct, that's all that matters. Now the question is, do I want reduced row echelon form? I think I can get away with not using it. No, it's so nice. I have to use it. All right, 1, 2, 1. Sorry. I made a mistake immediately. All right, so I'm going to take row 2. No, I'm going to take row 1 and make it row 1 minus twice row 2, just to get rid of this. And that will give me a 0. This will become plus 6 is a 7. This will become plus 4 is a 0. Oh yeah, you can definitely do that. X2 equals lambda. I would let X3 equal lambda actually. So setting X3 equals lambda, you get X2 is equal to minus 2 plus 3 lambda. And X1 is equal to minus 7 lambda. Now I should translate that into a vector because the question was all about vectors. So really this is some vector plus lambda times some vector. I'll deal with the lambdas first. This is x3. This is 3 minus 7. And the constants tell me 0 minus 2, 0. All right. So that's my answer. Can I get this into Maple? Let's actually go back to Maple. All right, so the point was 0 minus 2, 0. And the vector, the direction parallel was minus 7, 3, 1. I don't think the preview works here. It just shows you this, which doesn't really help very much, but at least it sort of didn't pick up any syntax errors. I might as well do this for no solution was minus 7 over 3. There was more solutions at a third. And anything except for 2, 1 over 3, and minus 7 over 3. So a quick check to see if that was right. Yep, that worked. And I think you can really give this in any order. So I could put the 2 last. Just make sure you get commas. It seems to be programmed up fairly well. So doesn't really help, but there's a bit of a preview. Okay. Oops. Any comments about this, Sean?
No, not really. I like that solution. I guess there's one thing I thought might be worth pointing out, which you did already address, which is when we got to part B, it told us something that if we're not looking very carefully at the question, might seem wrong, right? It says there are infinite solutions when m equals 2. If we look just at that last matrix M7, it looks pretty. It seems obvious that if we just substitute m equals 2, there should be a unique solution, right? Now that, as if I were a student sitting this test, I would say that tells me something's gone wrong and I should look further up the page. The reason I mention this is because you might remember question 1, right, as in the rules page, which had the little feedback box at the bottom. When we went through all the feedback from students who had typed anything in that box, the vast majority of students were saying that they thought there was an error in this particular question because of the problem they thought they were running into in part B. So that's a bit regrettable, right? Because that means that the students thought there was an error, so they went to report it, and then they didn't really try to answer the rest of the question. And I just wanted to point out, in the end, you know, there wasn't an error in the question. There was more to do there. Students who thought that they'd spotted a problem should have been sort of looking a bit harder, right? I'm not guaranteeing that there won't be errors in the solution, but we, of course, strive very hard to make sure, sorry, in the question, but of course we strive very hard to make sure there aren't any errors in there. And so you shouldn't assume the worst, right? Don't run into something that looks wrong and immediately report it as wrong and stop attempting the question, you know?
Yeah, we have a 5-stage check, I think. It has to be checked once and then again and then again. So there shouldn't be problems. There's always a slight risk with randomized numbers, but we're fairly good at this now.
Yeah, true. I'd like to think so anyway, yeah. But yeah, so in the case, let me switch over. Can I just check, am I coming through clearly on the audio? Because I'm getting told I have a bad connection.
You sound okay to me.
Okay.
Can -2 an answer? I don't understand the question. No, because everything, I mean, the row reduction was perfect. This step is fine if m is equal to -2 because it's, I don't know, something over like 1 over -7. You're dividing by -7. That's perfectly legitimate. This would be 1 over 4. That's also perfectly legitimate. So this matrix, this is valid for m equals -2. This is a valid row reduction for m equals -2. It's not a valid row reduction for m equals 2 or m equals a third. That's the only two cases where the information you get here is not valid. Okay, but what about this? Yeah, so yeah, I'm not sure. It would be 4. Well, I mean, you can try it. Try the row reduction yourself. If you're really, really concerned, go back to the original matrix, substitute m equals 2 and row reduce it. You will find it is actually, sorry, m equals -2 and reduce it. You will find it is actually this matrix for that case.
Yeah.
There are no problems with m equals -2.
Yeah, as Josh pointed out, the only dangerous row reductions are those divisions by potentially 0, which rules out it rules out m7 working for 2 and 1/3. That means that when you replace, if you substitute m equals -2 into m7, or if you substitute it into m3, or if you substitute it into m, you're still going to get the same solution set back, right? It doesn't matter that a 0 turns up earlier than you expect somewhere in m3, right? In fact, if you look at the third row, if you replace m with -2, then you still, like, the second column will still be a leading column, right?
Yeah.
You just would want to swap rows 2 and 3, I guess. But
yeah. So if m equals -2, this is leading, that is leading, this is leading. That's it.
Yeah, I guess you can, the sort of moral is you can trust Maple most of the time, right? It is doing the hard work for you for all m except m equals 1/3 and m equals 2.
Yeah, well, that's just because we did something silly.
Yeah, exactly. Yeah.
All right, maybe we should move on to the next question.
Yeah, let's do that. And I think this one will be very quick, actually. All right. So for this question here, it's actually a pretty short one. It's only worth 2 points. I probably don't expect to spend too much time on it, right? If I'm sitting the exam. It's asking about the determinant of a matrix. I've been given the determinant for a particular matrix, right? And I want to find the determinant for some other matrix that looks a little bit like it, but there have been some adjustments to it, right? All this seems to imply to me that this question is all about what happens, how does the determinant change when I apply elementary row operations to it, right? So we're talking about the determinant of this matrix here, B, C, A, E, F, D, 3H, 3I, 3G. But I noticed that it looks a little bit like the matrix that we've been told about here when it's just A, B, C, D, F, G, H, I, right? So it makes sense to try to manipulate this matrix here so that it looks a little bit more like this one here. Because I can't really do anything else with these values A, B, C, D, E, F, etc. Right? I don't know anything about them except that they're just real numbers. So how can I go about doing that? Well, it makes sense to apply some elementary row operations, right? The first thing I notice, I think, is, well, I sort of noticed two things. I noticed that the third row is multiplied through by 3. And I also noticed that if I look at the top rows here, the top row of this first matrix is ABC. The top row of this second matrix is BCA. It's kind of been rearranged a little bit, right? So I think I'll deal with the rearrangement first, actually. So I noticed that I would like, for example, I would like A to be the first entry in the first row, just like I would like D to be the first entry in the second row, etc. Really what I want is I would like to swap the third column with the first column, because that will make the new matrix will have a first column that looks a little bit more like the first column in the original matrix. So I would like, I'd like to swap columns 1 and 3, because that will give me this matrix here. But I just have to be careful about what's happening to the determinant when I do this. So if I swap 2 columns, can anyone remember or remind me in the chat, how does that change the determinant, if it does at all? Yeah, exactly, Hugh. The side change. So I'm multiplying through by -1 essentially. So the determinant of this matrix here is minus the determinant of this matrix here, the one that I get by swapping 2 of the columns. Okay, so that's all that's happened so far. It's looking a little bit more like my original matrix. Next thing, I think I'd like to swap columns 2 and 3, right? Because then my top row will be ABC, just like it was in the original matrix. Yeah, you might remember. So yeah, usually we talk about elementary row operations, of course. But you might remember, I think it was the very last lecture that we did in algebra. We said that we're talking about determinants because the determinant of a matrix, or the determinant of the transpose of a matrix is the same as the determinant of a matrix. Then anything you do to rows in A, any elementary row operations you apply, have corresponding elementary column operations in the transpose. The determinant won't change. Or it will change in the same way as it would have if you applied those row operations to the transpose. Okay, so anyway, next thing I'd like to do is swap rows 2 and 3. Sorry, columns 2 and 3, right? So I'm making a swap. That means I'm going to multiply by -1 again, right? So I guess if I want to make it super clear, I could write -1 times -1 times, right? But really, it means that I'm getting back the positive determinant. The multiplier is just 1 now at this point. Okay, now this looks almost exactly like my original matrix, right? Except that the bottom row is 3 times what it should have been. So the last thing I'd like to do here as a row operation this time is I'd just like to replace row 3, row 3 with 1/3 of that. So multiply it through by 1/3, right? And can someone remind me, what does that do to the determinant? Yeah, it scales it. And you just need to be a little bit careful here about which direction, right? Does it mean that, this is just one, I'll just ignore it, right? So does it mean, am I talking, so it's something times the determinant, right? Is it 3 times it or 1/3 times it? This is something that I think, well, I always get a little bit worried that I may or may not be doing it the right way. I might think of it as the determinant of this thing. If I multiply a row through by 3, it will be tripled, right? So the multiply should be a 3, is what's happening. So I sort of think of it as the determinant of, let me make it clear what I'm actually pointing to here. The determinant of this matrix. If I multiply a row through by 3, for example, right, which would give me this one here, then I'm also multiplying the determinant by 3, which means that the determinant of this thing is going to times the determinant of this original matrix. Okay, if that makes sense. So if you prefer, you can think of it as saying, I multiplied the row by 1/3, so the new determinant is 3, like is the inverse of 1/3 is 3. So sorry, 3 times the new the determinant of the new matrix gives me the determinant of the old matrix in terms of this being the old one, this being the new one. It's always a little bit tricky to refer to lots of things without names. I think if I were rewriting this question,
I think also I
sorry,
might
go ahead.
say it as like, because when you did this for operation, that thing scaled down by 1/3, but the number you're talking about hasn't changed. So if you want to calculate it, you need to triple it all back up. So that 3 sort of
Sure,
corrects
yeah,
for
yeah.
the thing you've done.
Yeah, yeah. That's a nice way to put it. Okay, and now I'm done, right? Because if I just check back up here, I was told, whoops, up here, I was told the determinant of that matrix is 1/3. So this is 3 times 1/3, which is of course 1. Okay, so my answer is 1. This question, it asks for a number answer, right? But it also asks for an explanation. So I could probably guess that that's going to be worth the extra point out of the 2 points total. So I should be careful about how I write up my explanation as well. What do I want here? Where did my maple session go? I mean, my maple TA go? Has it gone? Oh, sorry, here it is. Cool. Okay. All right. So so I think my answer is 1, right? But I need to justify this thing, and I should be careful about how I'm writing this up because I know this is marked by a human, right? So you can think about how you might have done it yourselves. But it looks to me like there's 2 important things I should mention, right? There's the fact that I swapped columns a couple of times, and the fact that I multiplied a row through by a scalar. So I might say something like, swapping 2 columns changes the sign of the determinant. Or in fact, I'll start by saying the second matrix can be derived from the first by doing the following operations. And what are they? So we did swap columns 1 and 3, then swap columns 2 and 3, and then multiply row 3 through by 1/3. Sorry, by 3. If I'm going from, if I'm making the second from the first. I think that's right. Let me just check in my head. Oh no, so I'm maybe I should just change it. So the first we derive from the second. Then it can match up with what I actually wrote in my working. All right. So now I just need to justify what happens to the determinant in each of those steps. So swapping 2 columns changes the sign of the determinant. Since this is done twice, the sign let's say the determinant is multiplied minus 1 times times minus 1, which is just 1, right? And then scaling row 3 by 1/3 changes, okay. I'm being a little bit more careful about my wording than I probably need to worry about for this sort of situation. But yeah, so I'll say a determinant, sorry, a matrix with a row that is 3 times the, what's the best way to word this? I'm not sure. Yeah, I'll leave you definitely in the details, right? But something like this, right? Yeah, let's do this. I'm scaling row by 1/3 multiplies the, well, scales and scales for now. But they're sort of scaling in opposite directions in some sense, right? I'm trying to keep track of what's happening in my line, my column of equations here, right? But I'd probably go back and to just the other direction. I would start with the determinant of A, B, C, D, F, G, H, I, and work towards the determinant of the matrix I want. But yeah, so in this, just to make it clear what I really mean by scaling, so in this case, the determinant is multiplied by 3, is what we'll say. Yeah, so altogether, the determinant will be -1 times -1 times 3 times 1/3. Something like that. And again, this is probably more than is needed for the 1 point for this answer, right? But the 2 things I really had to address were the fact that 2 swaps happened, right? So even though I swapped 2 columns twice, which meant that in the end, the sign was changed twice, so it sort of looked like there was no change to the determinant. But I better mention that happened. Otherwise, I haven't fully explained how to get from one matrix to the other, right? So even though it didn't really change my answer, it was necessary to actually find the answer. And then the other thing I have to talk about is this scaling the row by a factor. And I guess, sorry, I forgot to zoom in or make the font larger. But so something like this, I think should be sufficient.
Yeah, I think there are other ways to explain it as well. I mean, at some point, if you start with the P, that determinant, when you do these row operations, you end up with the quantity which is 1/3. No, sorry, you start with Q. When you do these operations, you end up with a quantity which is 1/3 of Q and is also equal to P. So you could end up with 1/3 Q is equal to P. There wouldn't be equal signs in my explanation. So you get 1/3 Q is P. That means P is 3. Sorry. Q is equal to 3P. It is kind of hard to explain because you have to sort of relate these 2 things.
Yeah, that's a good point.
We'll do our best to read whatever's written.
Yeah, and I'll point out that the way this question was marked, it was, as is often the case with these sort of wordy explanations, it's marked quite leniently, right? We're really just looking for you addressing these 2 things, the swapping of columns and a multiplying through of a row. And then if you got the correct answer here, that means you know what happened to the determinant in each case. So that's probably all a marker is looking for, right? As well as, you know, an argument that actually makes sense or doesn't contradict itself or anything.
Mm-hmm. We should probably get the last algebra question done so we can take a break and then continue on Friday.
Sure. It's kind of a big one, right? I was wondering if it makes sense to hold it off for Friday, since we won't be talking about the introduction and all of that. I mean, it's up to you and the students, of course.
Well, I'd like to just get this one done. That way we're not sort of doing even more on Friday. I feel like this question's not as big as it looks, so we'll see.
Yeah, sure, go for it.
Oh, sorry, I'm trying to. Right, now this question, I think, I'll just double check I'm looking at the full question. Yep, I'm too fast, it complains. Yeah, so that was the full question. So this question is worth 8 points, and it's probably because it is an explanation-based question, so we can really look at your explanations. Now you're given two planes, one in parametric vector form, this is pi1, and another one in Cartesian form. Now you actually need to read the first part of the question A because it gives you a very big piece of information. The planes are parallel. And the first part is actually just you have to explain in words how you would actually check that this is true. Now, let's just have a look. So what would I do to check that this is true? Well, I think I like checking the normals of planes. So what I would do is I would take the cross product of, and you can use, I'm happy if people use maple notation for the vectors here, it's very nice. I would take the cross product of this and verify it is a scalar, let's be very careful, a non-zero scalar multiple of the vector 2, -6, 5. Now, why am I doing that? This is because there is a, well, actually, let me change this. To get a normal to plane 1, I would then verify as a non-zero scalar multiple of this. This is because this is a normal to plane 2. I think that's actually sufficient. That's what I would do. You don't have to do any calculations. Say this is what you would do. This would verify that they are parallel. Now you don't need to do that final comment, but just for completeness, there it is. And those 4 lines, that's what I think I would want as an answer. Part B, there is a point of the form 2, 1, z naught, which belongs to plane number 2. Find z naught. Now in this case, well, I probably need some scrap paper, so let's go to OneNote. So what do we have? It's kind of very nice because they told me 2 of the coordinates, so I need to find the third compatible coordinate. So I want to have 2 times 2 plus 6 times 1 plus 5 times this missing z naught is -3. So that is 4 plus 6 plus 5z naught is equal to -3. So I'm getting, oh no, I did make a mistake, it's a minus sign. Okay. So minus signs, I can't work with them. Add 6, that is, let's see, so I get 4 plus 5z is equal to 3. 5z is equal to -1. Z is equal to -1/5. I believe that's correct. So it is just a number. It's -1/5. I wouldn't put -0.2 just in case. I think 1/5 is better. And then it says find the shortest distance between these planes and enter it in the box below, and then explain how you did it. Well, what do we have? Now I do want to make sure I've gotten the right point. Yeah, I have gotten the right point, good. So what do we do? So what they've told us is that these planes are actually parallel, and that's very helpful. I guess if they weren't parallel, it'd actually be even nicer because then the distance between them is 0. But what we have, so I'm going to look at these planes from the side and say I have a point on the first plane. I have the point. Now, do I want to use the point they've given me? I don't really think I do I? I guess I will. So they've given me a point. I might as well use it. The point 1, 2, 1, minus 1/5. And I have another point. This is plane number 2. I have another point on plane number 1, which is just the point minus 2, minus 2, 2. That's just reading off this point here. All right, so I have a normal because I can actually read a normal off the equation. The normal is 2 minus 6, 5. And what I really want is I want the projection of this vector onto this one here. So that's what I'm going to calculate. I just want to calculate, well, I even just want the length of this. So the length of this projection is a well-known formula. Let's give some names. Let's call this A. Let's call this N. So as we saw in lectures, the length is going to be A dotted with N over the length of N. Now, if you don't remember that formula, because personally I actually remember the following one. I remember A dot N over the length of N squared times N. And then when you work out the length of this, it just gives you this formula here. So that's nice. I need to do one dot product and calculate one length, and then I'm done. So what will this actually be in terms of the numbers we have? So let's just work out what this vector A is. It's going to be the vector minus 4, minus 3. And this one's a little bit hard because it's minus 2, minus... No, sorry, I've gone the other way. It's 2 plus a fifth. Or in other words, it is 10 fifths plus 1 fifth. It's 11 fifths. Okay. So this length should just be, all right, 4 minus 3, 11 fifths, dotted with whatever the normal was, 2 minus 6, 5. Okay, that was very nice. Those fifth and that 5 cancel out. So I'm glad I didn't try to be too creative. Over the length of, well, 4 plus 36 plus 25, the root of that. Absolutely values. So that is 8 minus, let's see, 18 plus 11, absolute value of, over the square root of 40 plus 25 is 65. Which is, so 8 minus 18 is just minus 8. No, it's not. It's minus 10. Minus 10 plus 11 is just 1. I'm getting 1 on root 65. So that's my answer. It is 1 on root 65. And then I actually have to explain it. All right, now the cross C, let's just see if I got that right. Even if I didn't, I would move on. Oh, I got it wrong. Curious. Oh, what did I do wrong? Oh, is there 2 minus signs? You are correct. So 18 plus 8 is going to be 26. 26 plus 11 is going to be 37. Sad thing that you don't have this available in the exam, but it is what it is. Still wrong. Oh well. I'll come back to that and calculate it later. So I've done something wrong. I'm not sure what.
Yeah, I think Henry pointed out there was a typo when you transcribed A or something.
That is probably possible.
Yeah, it looks like it should be, the first component should be -4.
Which?
So in your diagram, where you've got a vector A,
Oh,
in the diagram it's -4, -3, etc. When you
no, I
calculate.
see. I see.
Yeah.
When I calculate, it's different. All right. Well, the logic is right. Sadly,
Yeah,
these
and
ones
this
can't check
is what
logic, and this is
the final part is for, I think.
yeah. So even if you get that calculation wrong, you still get the marks for knowing what you were doing. So the question is, how do we explain this? So do not need to show any calculations. So I took a point, let's say A, on plane 1, and I took a point B on plane 2 and constructed the vector AB. I then projected this vector onto the normal, well, the vector. I can actually say what this vector is because it's something that doesn't require any calculation. 2 minus 6, 5. 2 minus 6, 5. As this is a normal to both planes. Technically, it's a normal to plane 1, but they are parallel. We've sort of been told they're parallel. As this is, I want to be cautious, as this would be a normal to both planes. The length of the vector I got is the shortest distance between the two planes. Took a plane A and A, B. The length of the vector I got. I think that's fine as an answer. It says exactly what I did, and it is correct. Any comments, Sean?
No, that looks good to me. I will point out, I just thought I mentioned a couple of common errors I saw with this question in particular, because for some reason there were lots of places for people to make mistakes. So one thing in particular that I wanted to point out is just the part you're doing here now. Quite a lot of students, for some reason, put in the correct distance, but then didn't give an explanation. And the way the marking scheme worked out here, I think, if I remember correctly, I think you got 1 mark for getting the distance right, and then there were 3 marks up for grabs for giving the right explanation. So don't think that's an optional box, right? Don't think that, oh, I know I found the distance, so I don't need to explain how I got it. It's there for a reason. It was worth quite a lot of points, actually, for this particular question. So you want to make sure you're actually, like, if you're asked to explain something, make sure you're explaining it, right?
Yeah,
Yeah,
I especially think we do value your understanding over the actual calculation, especially
exactly.
because it's, as you saw, I made the mistakes in these calculations twice. If I wanted to know if you could calculate it, I would probably give it to a computer instead of a student. Right, so we'll stop here.
Yeah, sounds good.
Do different methods get marks? Actually, this is probably an important question because I'm sure there were people using outside knowledge.
Yeah, that was it. So for this particular question, so remember last term the tests were closed book, which meant we were not expecting you to use you know, algorithms or rules that you that hadn't been taught in the course. It seemed like quite a few students answered this particular question. They found their distance by asking Google or something and finding a particular, a very nice formula, but one that's never taught in the course to find their answer. So when it came to explaining their method, they said, I plugged it into this formula and that did not earn any marks.
Yeah, if you can't explain how the formula works, because we have been teaching you how this works. We have been teaching you how projections and how all these things can be used to get this.
Yeah, so I think personally, if I write this question, I would have made it super clear. I would have said, explain geometrically how you would find this distance, just to make it super clear that just saying I plugged it into a formula is not going to get you marks.
Well, I would probably go even further and say explain using projections. Like,
yeah.
Like some of the questions may be worded in such a way. If they say do it, explain how you do it this way. They're not really looking for other explanations. They want you to do it the way they're saying.
And the other magic word, like certain words like hence or therefore, imply use what you just did to explain your answer. Don't come up with a completely different approach.
No, I think that's okay. We expect you. This is like a. Oh, sorry, that's not it. Where is it? Oh, here. This is kind of a very common application of projections, finding shortest distances. So we would expect you to have seen this sort of discussion before. So yeah, you wouldn't have to explain why it gives a shortest distance, just that. Just be using it in the correct way to get the shortest distance, I suppose. All right, well, that was quite long, and we still have the calculus stuff to do on Friday.
Yeah, I think calculus will be a bit quicker, but who knows? Oh,
Yeah, I should point out, this does take us longer to do here because we are spending a lot of time explaining things. During the exam, you'll just go, getting them out.
Yeah, you certainly, most of these, of course we have these explain boxes, but most of the time you don't need to write out, I use the vector theorem because blah, 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 because you're just finding the number or whatever. The other thing I was going to quickly point out was the earlier part of this question that said show the two planes are parallel or something like that. To do that, there are many ways that you could have done it, I'm sure. And you wouldn't be penalized if you didn't do it the way Josh did, right? So in that case, it doesn't say prove using a particular method that the two things are parallel. So yeah.
I was thinking another thing I could do is put this into parametric. I can make a parametric vector form for this and double check that these vectors are in this, like, well, they can be written in the terms of those vectors.
Yeah, check they have the same span. I think that makes it a bit tricky, actually.
Yeah, that's actually much harder to explain. That's why I didn't think of doing it that way. This seemed like a very simple, straightforward way of doing it and very easy to explain.
My favorite way of doing it, which I like only a handful of students did it this way, but you can easily read off the normal to plane 2 because it's in Cartesian form. And you can easily read off two vectors that are parallel to plane 1 because it's in parametric vector form. So you could just check that the normal to plane 2 is perpendicular to both direction vectors for plane 1 by verifying that both their dot products are 0.
Oh,
and
that's
then
nice.
Yeah, and you don't worry about finding the cross product.
Yeah, so this is just one way of doing it. Actually, yeah, that's quite nice. I didn't think of that.
Yeah, I think it's the least obvious approach, but it turns out to be the most straightforward in the end.
All right. All right, well, hopefully we'll see you again on Friday for the final live stream.
Oh, and we should also mention, I think my experience survey closes tomorrow morning. Is that right?
Does it? Yeah, so if you haven't filled it in yet, please try and fill it in. The response rate for maths has been very, very low, apparently, compared to the rest of the university. We would like to actually, I mean, we do value your feedback because it does shape how the course is taught in the future.
Yeah, so it closes tomorrow. I don't think it says what time. You probably have all day to do it if you haven't yet. But yeah, thanks everyone. Yeah, no problem, Adam.